nanohub.org.
Okay, so this, I guess, is the first talk of the sub-theme, which is the graphene colloquium that we are having. And what I'll be talking about, though, is somewhat more general. In fact, some of you have heard some parts of it before, and there's a lot of material on this on the NanoHub also. But the reason we are going over this is that it's particularly useful in terms of understanding current flow in graphene. So although the material itself is much more general than graphene, really, but it gives you this philosophy of this electronics from the bottom-up approach. And as I said, it's particularly useful in understanding conduction in graphene. So the basic problem then that we want to talk about is that we have some conductor, that's what you'd usually call the channel, across which you have made two contacts, you call them source and drain, and you put a voltage across it, and this voltage, what it does is, it separates the electrochemical potential in the two contacts. At equilibrium, all contacts would have the same electrochemical potential. You've put a voltage, one side's gone down, one's up. So you've got two different electrochemical potentials. And you want to find out how much current will flow. And one of the first things, as you know, you should do is try to draw what you might call an energy level diagram, something that tells you where the allowed energy levels are inside this channel. And what I've sketched here is some general density of states, this D of E. So this axis is energy, and it tells you the density of states, and I've sketched some generic density of states. So typically you have some non-zero value up to here, then you might have a band gap of sorts, and then you would have some density of states down here again. Okay. And current flows if there is a density of states available around the chemical potential. And the other thing I've sketched here are the two Fermi functions. That is, when you separate these electrochemical potentials, because each electrochemical potential actually describes a Fermi function. And this Fermi function you have seen before looks something like this. And for mu1, it changes from 1 to 0 right around mu1. For the other contact, it changes from 1 to 0 right around mu2. Everything below this is filled, above it is empty. Now, why does current flow? The way I think about it usually is that this contact wants to fill up these states because it's below the chemical potential, wants to fill them up. This contact wants to empty them. And so what happens is it keeps filling it up and it keeps pulling it out. And that's why current flows. And that's why if you don't have any states here, no current will flow. Why don't these states contribute to current flow? Because that is one question that often comes up and causes a lot of confusion, is that should these states contribute? And what I'd like to argue is, in general, not really. Because when you consider a state down here, this contact wants to fill it up. That contact also wants to fill it up. So it just stays filled. Nothing else happens. That's all. You see, the reason current flows is that as far as these states is concerned, the two contacts have two different agendas. One would like to fill it up, one would like to empty it. That's the basic. Okay. Now, the usual way of thinking about current flow, though, the formula that you are probably familiar with, that's this one. That's the Drude formula. And this is what is usually what you carry in your head. Like if you're trying to understand conductivity, you'd say, well, it's proportional to the electron density and it's proportional to the mobility. And where does this formula come from? Well, the way you usually think about it is that if you think of electrons inside this material, the Newton's law would say that dp dt is the rate at which the momentum changes is equal to the force exerted on the electrons. And I'm not worrying about this minus sign. So, I mean, you could put that in there, minus q, but you could think of q as being a negative number for this discussion. So it's dp dt is equal to the force. Now, if you believe that, then of course the momentum would keep increasing with time. What you say is inside a solid, that's not what happens. There is always some scattering term that does this. And so there is always this friction. And so at steady state, you can drop this. And so the momentum is equal to q over tau, q tau times e. times the electric field. And then how do you calculate the current? Well, the usual approach is you write current is equal to Q N V. This is the general equation for calculating currents. It is the charge on an electron times the electron density per unit length. It's the linear density of electrons times the speed with which it is moving. So if you want to calculate current there, you see you need the V, and so you put from the P you try to get a V by putting a Q tau over M. So typically this is how you would, when you put this V in there, that's how you'd end up with the Drude formula. Now I've written here NS because this is the electron density per unit area, whereas what I've written here is like the electron density per unit length. So what you could do is write it as width W, I'll call this the width, this is the length, call this the width times Q NSV. That is electron density per unit area times the width would be like electron density per unit length. But this is the one that you normally use to get the current. Okay. So now the thing is that when you think of it this way though, there's a few issues that you have to note. One is, firstly, it gives you the impression that all electrons are moving. It looks like it's not just these electrons, but you're thinking that, well, I should be using all the electrons, which is actually not, causes some confusion, because as I argued earlier, current really flows due to these. Now, more importantly in the context of this colloquium though is that if you try to understand current flow in graphene, the first thing you run into is like what mass to use, because if you're at all familiar with this literature, you'll know that this is a material in which the EK relation is such that there's no well-defined mass as such. That is, when you look at the EK relationship, as you know, usual semiconductor have a parabolic relationship which you write as E equals h bar square k square over 2m. But that's not the way it looks like in graphene. It looks linear. It looks something like that. And then, of course, it's confusing because you don't quite know how to extract a mass out of that. So that would be the first problem you'd run into in terms of trying to apply this equation to graphene. Okay? Now, instead, so if you look in the literature, no one really tries to use this at all. Although this is the one that we all carry in our head, this is how you interpret experiments, this is how you think about things. Yet this is not what anyone applies though in this field. What they apply is something else, and that formula looks something like this. And this comes from, they say, the Boltzmann equation. So the equation you'll see most often in the literature, they will say that, well, what you get from the Boltzmann equation is the following. Q square times so this is the same Fermi function, and here, by the way, we are talking about relatively low bias. For everything we'll discuss, assumption is this voltage is small, so we're really talking of linear transport, nothing to do with any nonlinear issues at all. Okay. Now, so this F is basically what you'd have at equilibrium. That's the F that you use here. And this D is the density of states per unit area. So I'll usually define the density of states as the density of states just per unit length, as per unit energy, rather than as per unit energy per unit area. So what we'll do is divide this by WL. And by the way, there's a W over L out here. So this is what you would normally call the conductivity. And you say that this is what comes out of Boltzmann equation, and there's usually no simple explanation where it came from. See? But this is the starting point for a lot of the work in the literature on graphene. And this quantity, by the way, is what you usually might recognize as the diffusion coefficient. That is, I wrote here Vx square, that is this direction is x. And of course, electrons are going at all various angles, and when you do the angular average, then Vx square would be like half of V square. So that's what people usually do. They write that as V square over 2. So they take that and put it as V square. So this is the formula that you'd see widely used. And here you see you're not having to ask this question about mass. It's just density of states, diffusion coefficient. That's it. Okay. Now, the other point I'll note here is this philosophical difference. And that is that when it comes to this formula, the feeling is all electrons are moving. All electrons, you have this electric field, they're all moving. When you use this formula, that's not true. What contributes to this conductance is only electrons around the chemical potential. How do you see that? Well, you see, look at this derivative of the Fermi function. You see, that Fermi function looks like this. If you take its derivative, it's non-zero only right around here. That's it. So when you look at that important function in this integrand, regardless of everything else, the point is that function only peaks up right around here. And so when you do this integral, what really contributes is electrons with energy right around there, like I had argued before. That's what really should be contributing to the current flow. Okay. Now, another formula that you'll see in the literature, in fact, let me write a slightly simplified version of this here for our comparison. That's Boltzmann. So Boltzmann would be now I kind of simplified it a little bit. You see, this has an integral and all that in it. Now, for this discussion, I'm kind of simplifying it by saying, let's assume this temperature is low enough that that derivative is almost a delta function right here. What you can show is that the area under this curve is always 1. So in that sense, no matter what the temperature is, that area is 1, and if it's very sharp, you can think of it as a delta function. So what I'm saying is, let's assume it's kind of at very low temperature. So this is a delta function, and so this integral can be dropped, and all that contributes is this. And that's what I've written here. Now you might say, well, what happens if you go to higher temperatures? Well, what it means is, if you understand the conductance at some energy, then you can always average over energies to get the effect of temperature. And when you do that, what will happen is you'll pick up all kinds of these Fermi-Dirac integrals. You know, there'll be f half, f 3 halves, all depending on what you're calculating. And I'm kind of trying to keep out of that so that we can focus on the main thing. Good. Okay, so that's then the Boltzmann result. Now, another expression that you'll see in the literature often is the following, and that's this Landauer formula. And that goes like this. It says Q square over H, that's the quantum of conductance, times integral dE minus del F del E. And then there is a quantity that people call the number of modes per unit energy. And this is supposed to apply only to ballistic conductors. And so usually people say that, well, you know, if you assume that your conductance if the conductor is ballistic, that is, electrons get from left to right without any scattering, then we'll use a formula like this. Okay? But then it's not clear how to go between this ballistic limit and this diffusive limit. This is the one that's supposed to apply in the diffusive limit. Right? And what I'd like to describe to you is this bottom-up point of view, where you have a nice continuous way of going from the ballistic to the diffusive, and you can see clearly what's happening here. See? So again, if I focus on low temperature, so I won't worry about that integral and all that, then I can write G is equal to, now I think I missed a Q squared here. Q square over H times the number of moles. That's the formula. Okay. Now, let me explain a little bit as to where that modes come from. So the way you can think about this is the following. We're starting from this case of a ballistic conductor where you have electrons that are going through like this, and there are electrons, you have states. Half the states are going from left to right, the other half are going from right to left. And the idea is that you could write the current that is carried by the right moving states. See? Those, we could write it as Q times the electron density times the velocity. These. So you could write the velocity v of x, that's in the x direction, and this electron density, that we could write by saying that we have the density of states is d over 2, because I only want to consider half the states, the ones that are going from left to right, and I want the electron density per unit length, so I'll put a length here, and I'll multiply it by F plus. What's F plus? Well, F plus is a function that tells me how the occupation of the right moving states, how well they're occupied. Right? F, by the way, this F1 and F2, those are Fermi functions. Those are the equilibrium things in the contacts. Inside the device, it's a non-equilibrium situation. The positive going ones are a little more filled than the negative going ones. And so F plus tells me how well the positive going ones are filled. And then there's the negative going ones. Those are also filled a little differently. And that's why the current is the difference between the two. And you could write it this way. And you could write I is equal to integral dE. So this is at a given energy. If you just looked at Q and V, you'd get Q, that's the V, this times this, that's the N. And you have things that are going from left to right, and you have things that are going from right to left. And the difference, when you sum it over, you'll get through the current. That's the idea. Now, in the case of the ballistic conductor, though, the simplicity that comes is the following, and that's this observation that everything going to the right is really came from this contact, and so is basically has the same occupation as the Fermi function in the left contact. So this, of course, is a very important non-trivial thing, and I'll try to explain it a little better. And then the ones that are going the other way, they come from the other contact. So what you do is you'd say this is F1 and that is F2. And this, of course, is the important observation. And you can kind of see it's intuitive. It's like this. You see, electrons are going from left to right. So let's say, this is Lafayette and this is Chicago. It's like going from south to north. And let's say there's something important happening in Chicago, so there's lots of people trying to get from Lafayette to Chicago. So F1 here is almost 1. You got lots of people trying to get on the highway. And it's all ballistic in the sense once you get on the northbound lane, you can't turn around. You keep going. On the other hand, there's hardly anyone in Chicago wanting to come back at this time. See? So this is all empty. Now, if you looked on the highway, what would you see really? You'd just see all the northbound lanes filled up, bumper to bumper, all the rightbound lanes completely empty. That's what would happen. So that's exactly what you expect. You see, you could draw a picture something like this. If you looked at the occupation of these levels from left to right, this axis is the x-axis. At this end, you have F1, which I'm assuming, let's say, is 1. That is, these states are all filled at this energy on the left. And then as you go through this thing, it's all filled. And then somewhere inside the contact, of course, it goes down to 0. Somewhere inside the contact. And when you look at, so these are all the right bound or the northbound lanes. These are plus k states. And these are all the minus k states which are filled from here. They do this. And inside the contact, it matches again. Now, you might say, well, but if there are so many states there, how is it that once you get in here, they have all, the occupation goes down so much? The idea is that's what happens inside a contact. You see, because once you, it's like you got only 2 lanes here, but once you get to Chicago, it's like there's lots of lanes to get out into. So once you go out there, of course, it becomes just a normal thing. So that's the idea of a contact, is this dilution. Anyway, so this is what you'd expect inside a ballistic conductor. And because of that, you see, you can write the current very simply. You know, it's Q N V. N is the density of states, half the density of states per unit length, times F, that's like N times V. This is it. Okay. And so this leads us then to the ballistic current, which would be integral dE times M of E. Actually, put a Q here. And then put a F1 minus F2. So what I did here is, I've called this quantity M divided by H. So that's this number of modes that I talked about. That's the M that appears here, and I'll try to connect it up better. But basically, you see, it's the density of states times the velocity. So just as density of states determines electron density, when you want to calculate current, you need density of states times velocity. It's not enough to have a state there. It has to be moving. So that's why this is dV. So the expression for M then would be something like dVx over 2L. This is M over H. It's just dimensionally, this has the same dimensions as H. M is a number. It's a constant. So instead of that quantity, I've written here M. Okay. Now, how do you get to this conductance formula? Well, that's where basically what you do is this F1 minus F2. For low bias, we say that we are taking the difference between 2 Fermi functions, and you could write it as a this Taylor series type of thing, del F del E times mu1 minus mu2. And this integral dE minus del F del E and this M of E, and mu1 minus mu2 is Q times the voltage. And so current becomes proportional to voltage, and whatever's inside, that's then like the conductance. This would be the standard derivation of the ballistic formula. Right? So finally what you'd have then is conductance is equal to Q squared over H integral dE M of E times minus del F del E. And this is where, as I said earlier, I'm simplifying things by saying let's do it at low temperature. So that thing is just a delta function. And so you get the Landauer formula, famous Landauer formula. Okay. Now, the reason I went through this in a little more detail, because some of you, I'm sure most of you have seen this somewhere in some form, is this, that the question arises is how do you apply this Landauer formula to something that's not ballistic? Now, not ballistic basically means that, you see, once you get on the northbound highway, it's not like you have to stay northbound. You could continually turn around. In fact, there's a mean free path. Like so if the mean free path is 1 mile, it's like every mile a certain fraction will be turning around. See? So what you'd expect would happen, and this you can show, is that instead of going like this, the distribution would look something like this. This would continually go down. And if you look at the negative k states, it will continually go up. And inside the contact, it will again connect up. So the point is that you're coming in here, it's a bumper to bumper right here, but then most people change their mind and come back. So by the time you get a little further down, it's not quite filled as much anymore. The highways are a lot more empty. And what you can show is that, of course, when I want to calculate the current, I still want to use F1 minus F. I still want to use F plus minus F minus. That is, what is the difference in the occupation of positive going states and negative going states? That's what I still want. It's just that now this difference is only a fraction of what it is between the two contacts. So you had 1 here and 0 here, but now in the middle the difference is a whole lot less. So some fraction thereof. And what you can show is that fraction, this is like F1 minus F2 times a mean free path divided by L plus mean free path, where L is this length. So if the mean free path is very long, then that factor is 1 and you have ballistic transport. Then the difference is exactly equal to whatever you have at the ends. That's what we've been talking about so far. But once the length becomes comparable to a mean free path, that's when what you get is a whole lot less. Now the result, of course, is that the current here then, instead of being what I'd written before, is now reduced by lambda over L plus lambda. Now this version of Landauer formula is, of course, very well known. What I haven't seen as much is this version, which says that if you had a conductor that was a few mean free paths long, then you should reduce the conductance by that factor. And that's what I have not seen as much. And this is usually what I'd say is most useful when it comes to analyzing real experiments in graphene. Because also most of the graphene experiment is not like fully in the diffusive limit necessarily. On the other hand, it's not ballistic either. It's usually a few mean free paths. And what I'd say is, well, this would be a good way to analyze such things. Okay? And this mean free path, then, if I had to write an expression for it in terms of tau, because the mean free time, as you know, is this tau that entered the Drude formula. So mean free path would be velocity times the time. Only thing I'd add is that actually there's a factor of 2 in there. And that's because, you see, the mean free time is how far an electron goes before it gets scattered. And if you assume that the scattering is isotropic, so supposing you have an electron going in some direction, so mean free time tells you the time after which it's scattered. But then if it's isotropic, then you see the chances of getting back scattered. What I mean is all of these are like northbound lanes. The current is reduced, of course, only if you get scattered into a southbound lane. As long as you're scattered somewhere here, it really doesn't matter. So it's like only as if half the scatterings matter, which is why you usually put in this 2. That's it. Okay. So I'd say that from the Landauer viewpoint, if you proceeded, this is the expression you'd come up with. See? And then if you apply it to a long device, then you'd say, okay, let me drop the lambda here, drop the mean free path from the denominator, and you have a conductance that goes down as length, just as it should from Ohm's law and all that. And you'd have something looking just like that. See? Now, how do you connect these two things? Well, you can kind of see how it works. You could write this as, if I cancel the W, I could write it as Q square dVx over 2L So I'm taking this standard Boltzmann expression and just writing it out separately like this. And if you compare the two, then I'd say if I put this thing equal to m over h, and this is the lambda over L. That's basically the Landauer expression. That's it. The advantage, of course, is that this one is relatively harder to derive. So you have to go into the Boltzmann equation, and it takes a while to understand the Boltzmann equation, and then there's various approximations that go in before you get here. So it's a lot harder to derive, which is why the expression you usually carry in your head is more this one, not this one. Okay? And the other thing is, this only applies when you have a very long diffusive conductor. Whereas this way, you see, you have something that interpolates nicely between the ballistic and the diffusive regime. Just goes continuously. Now, what you might wonder is, how could it be this simple then? You see, because as I said, to derive this would be a lot more work usually. And I'd say that the assumption we made here, though, here is that electrons, as they go through from one end to another, they sort of retain the same energy. There is no inelastic scattering in the process. So, and that is why you can write the current. The key to our derivation was that we wrote the current as integral dE times something times F1 minus F2. This was, of course, the key point. And once you have F1 minus F2, then we went to the linear response and got all the other stuff. But the thing is, this expression doesn't really apply to a very long device with lots of inelastic scattering. You can convince yourself of that. That, if this was a real long device with, lots of scattering, you could put 10 volts across it and it would still be in linear response. Of course, 10 volts across say a 10 kilo ohm resistor from Radio Shack, it's still linear. But if you take two Fermi functions separated by 10 volts and try to apply it, you'll just get nonsense. So this kind of a formula, this kind of formulation, you can really apply rigorously only to conductors that are relatively small, where you can argue that there's no inelastic scattering from left to right. See? Then how are we applying it to a big conductor? After all, this Boltzmann expression is supposed to work for big conductors. So how are you applying that? I'd say that philosophically, the way you can justify it is by saying that when you have a very big conductor, you can still think of it as lots of little things in series. And it is as if we are taking one of those little things, applying this kind of a viewpoint to it, extracting the conductivity from that. And then saying, well, if you put a lot of them in series, that's still, it's the same conductivity. And it seems you're doing it right. The part you can convince yourself is, this and this, they're essentially the same expression, right? But then, of course, the Boltzmann equation is more rigorous in the sense, as I said, the reason it's harder also is that you have to go through certain arguments, and you can show that this expression only holds when scattering is either elastic or isotropic. But if it is inelastic and anisotropic, then it doesn't quite hold. And I believe that in that case, some of the simple assumptions we have made wouldn't quite work. You see? Okay. But the other point I'd like to mention here is that the nice thing about this viewpoint, and this is kind of the basis of what we have been doing a lot in terms of our bottom-up viewpoint of all this, is that bottom-up viewpoint means instead of trying to take big conductors, and where Boltzmann equation is applied and all that, and then trying to figure out what happens in small things, we do it the other way. Start with small things and go upward. And what we believe is when you take your experience from big conductors and project it down, it unnecessarily complicates the story a whole lot. And so if you're really interested in small conductors, this is of course a whole lot simpler. And the point I was trying to make is it even might give you a lot of insight into big conductors as well. And this is particularly true of things like thermoelectricity. That's something I won't have time to get into today. But as you know, in conductors, one way to drive current is, of course, put a voltage across it. But another way to drive it is to put a temperature difference. One end is hotter than the other. And one of the very interesting results that I'm sure you all know is that if you put a hot probe and a cold probe, then which way the current flows depends on whether it's N-type semiconductor or P-type semiconductor. That's an experiment, actually. Even I have done this. And it's a very nice, simple result. And yet, trying to understand why the current flows in the opposite direction is not very easy. See, if you think about it. Why is it that in p-type semiconductors, the current actually flows in a direction that's opposite? On the other hand, if you take this expression and just look at F1 minus F2, the answers will just fall out. See? It's just that the difference between the two Fermi functions now comes not from a difference in chemical potentials, but just from the difference in temperatures. That's all. Nothing more to learn. So it's sort of like once I've understood conduction, thermoelectricity and all that just falls right out of it. There's nothing else to, no new things to learn really, just fun. So there's lots of things where this bottom-up viewpoint, where you basically kind of start from here, essentially, and which applies to a lot of small conductors and even to some big conductors. And you can get all sensible answers that you can use. Okay. Now, to take this a little further then, I need to bring in EK relationships. That is, so far you see I haven't even argued about EK relations. I just said, well, you have some density of states. How do you get density of states? Well, usually for crystalline conductors, the way you do it is get it from an EK relation. Okay. Now, the first case you might want to consider then would be a one-dimensional conductor. So let's say I have a one-dimensional conductor, this direction, and we'd like to know what is the density of states. And the way you do it usually is that you assume any EK relation, let's say, need not be parabolic, could be anything. And the idea is that if you put it in a box, then the allowed values of k are separated by 2 pi over L. Right? And that comes from imposing this periodic boundary conditions. And as I always say, that it's not that any real solid actually has periodic boundary conditions on it. But what you believe is that in big conductors, it doesn't matter too much what actual boundary conditions you use. And so you can use whatever it is that is mathematically convenient. That's really the argument. Because physically, of course, you don't really, it's not in the form of a ring at all in general. Anyway, so this is just a way of counting the density of states. And the feeling is that even if you did the actual boundary conditions, things wouldn't change all that much, at least as far as big conductors go. Anyway, so it's separated by 2 pi over L. So if you look up to a certain energy E and ask how many states do I have, then the argument would be, then the number would be something like, so this plus k minus k corresponding to a given energy. That's the maximum. So what you first write down is the total number of states, which is 2k divided by 2 pi over L. So the idea is the total range is 2k, states are separated by 2 pi over L. So the total number of states in here is 2k divided by that, which is kl over pi. Now, once you have this total number of states, the way you get density of states is take its derivative with respect to energy. The idea is that if I increase the energy a little bit, how many extra states do I pick up? So you put d of E, and what you'd get is L over pi dk dE. And as you know, this dE dk, that's what is usually called this group velocity. That's the velocity you should associate with an electron in that state. So usually you should write it here because we'll be needing this more. H bar V is equal to dE dk. So that's a general relationship that does not depend on EK relations. Now I'm sure most of you have seen some versions of these things. The point I'm trying to do though is I'm trying to get these relations in a way where I do not use any special EK relation. Because remember, we are kind of always trying to do this because we want to understand graphene. And graphene has this EK relation which is not the standard parabolic one. So we don't quite want to use a parabolic relation in anything we are saying, because then it would be special and you wouldn't be able to use it for graphene, right? So this is general. Doesn't matter what your EK relation looks like, that's true. Similarly, what I wrote here, that's perfectly general. No matter what, this is still true. See? Okay. So when you do density of states, then this dk dE, that would be, I suppose, is this 1 over h bar v. So that was the KL over pi. Yeah. So now, if you want to calculate this number of modes, because in this way of thinking, of course, modes plays a very important role in this thinking. So let's say we want to calculate the number of modes. So it's equal to dV over 2L. So that's equal to d is L over pi h bar v, that's d. So I've taken all that in there, and then I need a v over 2L. So you'll notice the answer you get is, I guess this is m over h, dv over 2L, and so m is equal to 1. So for a 1D conductor, you see, originally I introduced this concept of modes as by saying, well, let's take a ballistic conductor, see what current flows through it, and what you get is something like density of states times velocity. And in all of this, of course, there's no h in the thinking, dv. It's all classical as far as we are concerned. We're just talking of some states with some velocity. It could be, as I said, cars on the highway. I mean, no h involved, nothing else. We're just taking the states times the velocity, nothing else. But then, now of course, we have brought in the EK relationship, which of course builds into it the quantum viewpoint, wave viewpoint, etc. And once you bring that in, then you can see this m, dv over 2L, for a 1D conductor basically becomes 1. It's like as if it's a single mode. See? And so that gives this concept, this mode, a lot more importance and significance. You see, in the usual solid state physics, you see a lot about density of states. That's what you usually see in the literature. Modes is something no one talked about till mesoscopic physics started, till people started looking at small conductors, where people started using this Landauer method, and modes started playing a very important role in that thinking. See? And what this shows is, this m is, when you put in these numbers, this comes out as 1. And of course, one of the most important experiments that happened like in the late 80s, which kind of helped people start using the Landauer formula, was this conductance quantization, where people took a piece of semiconductor, continually made it thinner, narrower and narrower, and showed that the conductance, instead of going down linearly as the width, actually went down in steps. It was more like this, where the m went as 1, 2, 3, 4, things like that, rather than as a continuous variable like that. Okay? And the general expression for m then, which is what I'll try to obtain next, what happens is, let's do this in 2D now. So again, I want to calculate m. For that, I need density of states. And so for 2D, we first write down the number of electrons that I would have if I were to occupy all the states up to a certain energy E. And in that case, the way you think about it is, it's a two-dimensional thing, kx, ky. And I'm assuming the EK relationship is isotropic. So the question we are asking is, if you go up to a certain maximum value of k, how many states do I have in here? Some maximum value of k corresponding to some energy. And then the idea is if I increase the energy a little bit, how many extra states do I pick up? That's the density of states. So N of E would be, this pi k square. That's the area of that circle. And then you divide it by the density of states. And the states, of course, in this direction are spaced by L over 2 pi, in this direction by W over 2 pi, whatever the width is. So you basically have W over 2 pi, 2 pi over W and 2 pi over L. And that then comes to L W k squared over 4 pi. So that's the total number of states. Now, if you want the density of states, you'll get, I'm supposed to take derivative with respect to energy, so LW 4 pi 2k and then dk dE. Now at this stage usually you then invoke the EK relationship and do that, which I'm trying to avoid invoking, of course. So what I'll do is instead for dk dE I'll write h bar v. Now that way, that's general, that doesn't depend on EK relationships. So the expression you then get, let me write it on top, is that the density of states is LW over 2 pi h bar v and then a k. That's it. I've done this right. Okay. So you'll notice the density of states is proportional to k divided by v, and you see k is like momentum. So usually if instead of h bar k you write mv, then you'd get the standard parabolic band density of states and all that. That you could do if you wanted. But as I said, that's what I'm trying not to do. Now if you want m, number of modes, then I'd use this relation. And this is where, of course, what appears here is the velocity in the x direction, and I want to replace it with the net velocity. That means you got modes in various directions which have different components in the x direction. And what you can do is, if you average it, again assuming this is a big conductor, so I don't have to worry about graininess, just average it. So if you average over that angle, then what you'd find is instead of Vx, you could write 2V over pi. This 2 over pi is what you get by this angular averaging of cosine theta. So I think what you should get then is, try out, h over 2L, and then the d is whatever I wrote there, L times kW over hv. 2 pi h bar is just h, and then 2v over pi. And I think this should be equal to, if I've done this right, kW over pi. So this would be another way of thinking about the number of modes. Indeed, this viewpoint is usually more well known. This is the way you think about this is, you've got a certain width, how many wavelengths fit in? Because you see, k usually you think of as 2 pi over the wavelength. So this kind of tells you that in a given width, how many half wavelengths actually can fit into it. And that's the viewpoint that comes naturally if you're thinking of it from the point of view of microwave waveguides. And that's how usually people think of modes. And which is kind of nice, and what it shows you is that number of modes really depends on k, again in kW over pi, irrespective of the EK relationship. Again, remember I avoided using that, you see. So this is true no matter what. Doesn't have to be parabolic. This is what you'll always have. See? And this viewpoint, of course, the reason I kind of started here is because this is the one that comes naturally. It doesn't even require you to know quantum mechanics. This is the one that comes by saying, well, you're just counting states finding the current in a ballistic conductor is density of states times velocity, etc. That's what comes naturally. You see? And what I tried to show you is that that is what will also give you this other viewpoint of what modes is. See? Kw over pi. Now that then leads you to a natural way of thinking about the conductance. You see, so let me write this up here. So I'll write it here, m of E is equal to Kw over pi. And let me also write the electron density. So as you know, the total number of electrons that we wrote up to a given energy, if all the states here were filled up to a given energy, would have been this pi k square. I guess I think what we had was WL times k squared over 4 pi. Right? That's what we had by this pi k square and then dividing by 2 pi over L and 2 pi over W. So this would be that. So you could write the electron density per unit area. So this is N divided by WL. You could write as k squared over 4 pi. Okay. So if you look back then, in this Gruder formula, conductance is proportional to Ns. And that thing is what you interpret as mobility. And so anytime you see any data on conductance, first thing you do is divide it by the electron density that you have measured and plot it and then ask the question, now what is this mobility? On the other hand, if you believe this formula, then the way you might want to interpret your data would be like this. You see, m is proportional to k, whereas ns is proportional to k square. So what you can easily show is that m is proportional to square root of ns. That's easy enough to see. You see? And so from this point of view, when you write the conductance, instead of being like ns times something that you call mobility, you tend to get square root of ns times this mean free path from here. You see? And the square root of ns is simply because it's proportional to the number of modes, and ns is proportional to k square, m is proportional to k. You see this out. So if you believe this, then when you look, when you measure conductivity, you'd want to divide it by square root of ns, and then whatever you get, you try to interpret as mean free path and make sense of it. Okay? As I said, what picture you carry in your head kind of determines what you do with your experimental data, really. You see? And what everyone does is, of course, this one. As I said, when they actually calculate things, they often use this one for graphene, but when they think, they usually think with this one. So I think in the handout, one of the picture, I think that's the last one in your handout that I have there, where I show that with the same data, if you plot the conductivity divided by ns, you'll get something like this as a function of ns. And of course, as you change the electron density, what you're really doing is changing the Fermi energy. You're changing the energy up to which things are filled. And you tend to see something like this, and you look at it and you interpret it as saying, well, the mobility is actually going down with energy. So more energetic the electrons, less the mobility. Right? That's how you'd interpret it. On the other hand, when you take that same data and divide it by square root of ns, you tend to see something that's more flat. You see? And you think that, okay, this is more like the mean free path, and it's constant with ns. Because when I divide by square root of ns with the right appropriate factors, which you have in the notes I gave you, I think the right factors are all there. But the point is, it look kind of flat. And you might say, well, why is it that this one's going down and this one's flat? After all, this is supposed to be the mean free path, and this is supposed to be q tau over m. That's the mobility. Now, usually you'd say, well, mean free path is like velocity times time, And when you increase the energy, what happens is the velocity is also changing. And so you could always have something where the tau is changing, but lambda isn't, just because of that. Except that in graphene, when you look at the EK relation, it's linear. dE dk is constant. It's the same velocity at all energies. And which is why often people say, well, the mass almost looks like it's infinite. It may put an electric field, the velocity doesn't change. Looks like something very heavy. Can't change its velocity, you see. Okay. So the thing is, from this point of view, you'd say, well, velocity is the same. So if lambda is the same, shouldn't tau also remain flat? And my answer is, well, what happens is, in this case, it is as if the mass is increasing with energy. And I'll try to explain why. You see, if you really want to interpret it in terms of mobility, then you ought to remember that the mass is not a constant with energy, but it keeps increasing with energy. You see, that's the point. So how would you show, why do I say that the mass is increasing with energy? So that's this last point I want to make, and then we can stop. And that is, if you equate these two viewpoints that we have here, if you say that I want to, and this of course is equivalent to that I've argued. If you say that I want this to give me exactly the same results as that in 2 dimensions, actually in 3 dimensions as well, then what you'd find is that the right way to define mass is equal to velocity divided by momentum, which is kind of different because normally often we think of mass as the expression that you learn, that we usually teach, which you usually would need to know for your qualifiers. You'd be in trouble if you use this one. What you should use to get through qualifiers is this one. See? And if you use this one, then usually you'd get a mass of infinite in this case, because in graphene, the velocity does not change. You see, momentum is proportional to k. P is equal to h bar k, of course, in this discussion. So in graphene, the velocity doesn't change with k. It's the same at all momentum. So based on that, this is 0, so m is infinite. If you use that formula, it doesn't look right at all. See? But if you use this one, then what you get is something interesting, and that is, you see, V, I put h bar k, and for graphene, E is equal to h bar V times k. And so what I could do is, for mass, I could try to eliminate this in terms of E. So what I would do is, let's say, instead of this h bar k, I could write E over V. And so that then will give me mass is equal to E over V square. So what that means is, as the energy increases, the mass also keeps increasing. For a linear relation, that's exact. Now, if you had applied this to a parabolic dispersion law, you would have got just the standard mass. It would be energy independent, there would be no problem. But when you apply it to a linear thing, if you use this relation where mass is velocity over momentum, 1 over m is v over momentum, this is the expression you get, which is kind of reminds you of E equals mc square, of course, kind of like that. And this is also the mass that people measured in cyclotron resonance experiments. Though why that's so, that requires some discussion. I won't go into it now. But this is the mass they measure. And what they find is, while in ordinary semiconductors, as you change the energy, as you know, the cyclotron resonance frequency is supposed to be QB over M. That as you change the magnetic field, the cyclotron frequency is something like this. And usually in a normal semiconductor, that's independent of the carrier density. If you change it, same mass, is fixed resonance. Whereas in graphene, as you increase it, the cyclotron frequency actually goes down. That's an experimentally measured fact. And to understand cyclotron resonance also, the same mass actually enters. And the main point here I'm making though, because we haven't really discussed cyclotron resonance, the main point I'm making here is that if you want those two things to be the same, if you look back at how one deduced the Drude formula, it was like from Newton's law you got a momentum and then divided it by mass to get the velocity so you could calculate the current. Remember, that's the first thing I did. If you think of that, you can see that the right mass to use is the ratio of velocity to momentum. And so if you use that, then of course you'll be able to interpret, you would be able to use this formula and interpret things. But the important thing to remember then is that this mass is not a constant, it's energy dependent. Whereas if you go at it from here, then of course mass never even enters your thinking. You can just go straight with density of states or something, or the number of modes, and that never enters. Okay? So that's the point I wanted to make here, though. I guess, as I said, the purpose of this talk was kind of twofold. One is just a general introduction to this electronics from the bottom-up viewpoint, and where I'd say, when you try to understand current flow, it's like you start from ballistic things and then ask what happens as you put in more complications, instead of the other way around, where you start from big resistors and then wonder what happened when you make it smaller. See? And what I feel is, when you do it that way, lots of things, including thermoelectricity and all kinds of other things, get a lot clearer actually. So that's the one general philosophical thing. In this context though, it's particularly relevant because to understand graphene, as I said, it's like you really get into some of these important issues where it's important to understand the difference between these three types of conductance formulas. This kind of summarizes this thing, right? So what I'll be doing in the next lecture after the break is we'll talk about the EK relationship of graphene and where that comes from, where this comes from and the theory behind that, right? Good. Thank you. Yes, please.
The question, which I could not understand the last 2 years when I started taking quantum mechanics classes, what is the origin of the term chemical potential? Is it an intrinsic property? How does it originate?
Okay, I guess the question is about the origin of the term chemical potential, right? Where does it originate? So usually I would think of it as, like, in general, if you have any density of states that you have here, so density of states at 0 temperature, we are generally accustomed to thinking that all the lowest states are filled, all the highest ones are empty. So there will be some line here that will then separate the lowest states from the higher ones. I think you call that the Fermi energy. Now when you raise the temperature, that's when I think you still have that demarcation somewhere. It's just that it gets a little diffuse, so that instead of having this very sharp thing like this, where everything here is occupied and everything here is unoccupied, it is kind of smeared out over kT, over a few kT, which seems reasonable, except that that of course needs discussion, why it is that way, where the Fermi function came from, etc. Those are things that need discussion. But roughly you'd say, but it doesn't seem unreasonable. I mean, at low temperatures it is all filled up to here, now it's separated out. And I think that standard terminology is that at non-zero temperatures, people call it a chemical potential, right? And again, to that I should add this thing that I think strictly speaking, what we are talking about should be called the electrochemical potential. Electrochemical in the sense that there's the electrostatic potential also. So for example, if I put a voltage here, like a positive voltage, that would lower everything, the entire density of states. If this was like under a gate where you put a positive voltage, makes it much easier for electrons to get in, all the electron energy levels go down. And if the electrochemical potential stayed right there, there would be a lot more electrons, which won't happen. Usually what would happen is it would want to stay neutral. And so just as this goes down, the entire level will go down somewhat. So I think people say that so this part of it they might call the location of this Fermi energy relative to the bottom, they might call the chemical potential, and the whole thing the electrochemical potential. But as far as I'm concerned, in our discussion, all we need is this electrochemical potential. And one point I do keep making often, and that is that you often tend to say that J equals sigma E. That is, current is driven by an electric field. And the point I make is that's really not true, because in a PN junction, there's an enormous electric field, no current flows. Current is really driven by sigma grad mu. And what really matters is the gradient in the electrochemical potential. So it will flow. What drives everything is because up here the electrochemical potential is high and electrochemical potential is low somewhere. That's really what is driving current. It's not electric field setup, really. Right. Yeah, that's the part. Yes. So the question was that now this idea that electrons want to go from higher chemical potential to lower, where does that come from? How did it? And I'd say that in thermodynamics, to me, it is kind of analogous to temperature. I mean, and just as deep, namely, just as temperature, you could ask, why does heat flow from hot things to cold things? Right? And a very important realization is that what really drives it is not the content of heat, but the temperature. So you could have, so for example, supposing you have these two materials, one has a density of states like that, and the other has a very low density of states, hardly any. And this has a chemical potential that's somewhere up here, let's say. And if you actually counted electrons, you'd say there's hardly any electrons here. There's lots of electrons there. But the point is the current will really flow this way and not the other way. So it's like when you write a diffusion equation, you often think that, well, current flow is gradient of the electron density. But that kind of the implied thing is that the density of states is the same. That's kind of implied there. So it's a more special thing. Because, as I said, if you had a very low density of states here and you fill it up to here, there's very few electrons here. And here there's a high density of states, but you fill it up to here. So lots of electrons there. But the point is electrons will still go this way. It's not driven by how many electrons you have. It's rather the degree to which it is filled. And in that sense, it is kind of like temperature. So I guess the question is that in the case of gravity, when something goes down under gravity, you can see where that force comes from. I mean, we understand that. See, in this case, what is it that is driving it? That is the question, right? And I'd say this is purely a statistical thing here, right? And I have sometimes used this word entropic force in this context, that in a way, why does energy go from hot things to cold things? It is just that if it flows that way, then energy always wants to distribute itself in as many degrees of freedom as possible. And what you can show is that by going from hot to cold, you make that possible in a way. So But that requires more discussion. So in that sense, it is not like mechanical force. The example that you used is mechanical force. And I've sometimes talked about this as being something like an entropic force. And lots of things in real life are really driven by something like this. Right? Now, in the case where the density of states is constant, then you have the diffusion equation. And then you would say, well, that's because you got lots of electrons here and very few here. So that's why they are going, just as if you had if you had a box where it was all filled on one side and the other side was evacuated, and if you suddenly remove the partition, it would just distribute. That's also an entropic force, of course, way it distributes. And in that case, you'd have said, yeah, lots of electrons here, it goes over there. So what's not so easy to understand is why even when you have less electrons, what really matters is the degree to which it is filled. So just as heat flow does not depend on the total amount of energy, but rather the temperature, which is actually the amount of energy per degree of freedom. That's KT really. So it goes from hot things to cold things because hot things have a lot more energy per degree of freedom.
Isn't that like the electrons energy, like higher the electrons energy, it'll prefer to go to a place of lower energy?
Prefer to go to a
place of lower energy, or it can be in a lower state of entropy, like the lower entropy being enforced everywhere.
Right. So the example I have sometimes used is the following, that take the simplest case, like say a hydrogen atom, something very simple with just 2 levels. So the question was, right, what it is that it's like, why does the electrons always want to go down, but normally not up, right? So for example, that's what we normally learn. And it's one of those things where, you see, beginning students sometimes ask me this question that, why is it that it always goes down and never up? But usually graduate students, by the time you're a graduate student, you probably stop asking questions like that. Not that it gets any clearer, but but if you think about it, it's really a very valid question. That, after all, this doesn't come from Schrodinger equation by any means. If you take, it's nothing to do with quantum mechanics really, because if you take the Schrodinger equation, anything that takes you down will also take you up. It's a Hermitian Hamiltonian. If you have a H12, there will be H21. Really doesn't help explain how you go down and never up. And the argument that I think in Feynman's statistical mechanics, it has this like on the first page actually, on the first couple of pages. And the argument he makes is this, that this is coupled to a reservoir which has a certain density of states. And the thing is, so if you look at the density of states, let's say it's something like this. Now, let's say the electron is here and the reservoir is somewhere here. Now, if the electron goes down, the reservoir has to go up. Overall energy exchange, it's conserved. And the reason it's much easier to go down than up is simply that all normal reservoirs usually have an increasing density of states. So if you have 10 states here, you'll have 1,000 states there. So it's like when you are going down, it is like you're going down to one level, but your reservoir has 1,000 levels. When you're going up, you're going to one level here, but the reservoir has only 10 levels. And so it's a whole lot easier to go down than up. So this is again what essence of this entropic force, that it's like, yeah, these reservoirs always have this, and logarithm of this density of states, that's what you call entropy basically, K log W, that's the thing. Right? But these are of course all very deep issues that require lots of discussion, right, to get it clear.
When we were using the Landor formula for ballistic transport, we had this conductance proportional to the number of moles. And when you went from Landor formalism to this non-ballistic mode, you multiplied that by lambda upon L plus lambda. So what happens even in a ballistic transistor, there is always a probability that you get into the drain and then scatter back. How do you take that into the picture? Because I see that you have scattering more within the channel, but not on the drain side. So you scattering is going on drain side, what's the probability of that getting back to the source? Is that also incorporated into this L lambda upon L plus lambda? Or?
No, yeah, in terms of what happens in a transistor at the drain, probably Mark has thought about this a lot more on this. But in general, in this context, at an abstract theoretical level, what I'd say is that what really defines the contact, what makes it very special relative to the channel, is the fact that here you have only a few modes, like say 10 or so, whereas here you have like millions of modes. So it is as if you have this a two-lane highway that suddenly opens up into lots and lots of lanes, right? Because this is the one point that Landauer always stressed very much, that, you know, the picture I drew, that where I said that there is a certain separation between positive going states and negative going states. But once you get into the contact, there is no separation. And people say, well, yeah, sure, once you get into the contact, it's all in equilibrium. But if you think about it, you see, current is the same everywhere. So if there is no difference between plus and minus, then how is the current being carried? And the argument really is that you got 10,000 modes in there or 1 million modes in there, and the slightest difference is enough to carry that current. So because you had only 10 modes here, and because you had 1 million modes here, you only need a small fraction of this separation to carry that same current. But that's really the essence of a contact. Right? But in a real device like a transistor, you know, where you can draw the line and say that this is a contact and that's a contact and this is a, that needs serious discussion always. Right? Whether it because this is an idealization that tells you that in any device, of course, somewhere there must be a contact of some kind. That's essential, somewhere. For practical reasons, of course, we would like to draw it as close as possible. I mean, in principle, you could always draw it somewhere up here, way outside, so include everything as your device and draw your line, you know, somewhere where you have put the solder. But for practical reasons, of course, you'd like to draw it close. And then the question is, what can you get away with? How close can you put it, really? But that, in the context of transistors, I think Mark has thought a lot more about it, so you should discuss it with him. Yes.
For the last equation you developed, E equals to mv squared. Actually, I think you're using that point as the energy reference.
Right. Exactly. Yeah. Though all I did was I was using this relation, E equals h bar v k. So something like this. Right. Right. You're right. So right, because this is 0 at this point. Right.
Actually, at that point, m equals to 0.
Right there, you'd say, based on this, the mass is 0.
And so at that point, n actually carrier density equals to 0.
Carrier density is also going to 0, yes.
How do you describe the conductance around it?
Right. Now, experimentally, what happens is as you approach the Dirac point, other issues get into the picture, like disorder and all that. Right? Whereas if you just do it theoretically, then I think it wants to blow up around there. Right? What you see. Now, though experimentally what happens, hard to compare directly with experiment, because around here, usually all kinds of disorder issues kind of don't let it blow up, essentially, right? Smooth it out.
nanohub.org.
Okay, so this, I guess, is the first talk of the sub-theme, which is this graphene colloquium that we are having. And what I'll be talking about, though, is somewhat more general. In fact, some of you have heard some parts of it before, and there's a lot of material on this on the NanoHub also. But the reason we are going over this is that it's particularly useful in terms of understanding current flow in graphene. So although the material itself is much more general than graphene, really, but it gives you this philosophy of this electronics from the bottom up approach. And as I said, it's particularly useful in understanding conduction in graphene. So the basic problem then that we want to talk about is that we have some conductor, that's what you usually call the channel, across which you have made two contacts, we call them source and drain, and you put a voltage across it, and this voltage, what it does is, it separates the electrochemical potential in the two contacts. At equilibrium, all contacts would have the same electrochemical potential. You've put a voltage, one side's gone down, one's up. So you've got two different electrochemical potentials. And you want to find out how much current will flow. And one of the first things, as you know, you should do is try to draw what you might call an energy level diagram, something that tells you where the allowed energy levels are inside this channel. And what I've sketched here is some general density of states, this D of E. So this axis is energy, and it tells you the density of states, and I've sketched some generic density of states. So typically you have some non-zero value up to here, then you might have a band gap of sorts, and M. So typically this is how you would, when you put this V in there, that's how you'd end up with the Drude formula. Now, I've written here NS because this is the electron density per unit area, whereas what I've written here is like the electron density per unit length. So what you could do is write it as width W, I'll call this the width, this is the length, call this the width times Q NSV. That is, electron density per unit area times the width would be like electron density per unit length. But this is the one that you normally use to get the current. Okay. So now the thing is that when you think of it this way though, there's a few issues that you have to note. One is, firstly, it gives you the impression that all electrons are moving. It looks like it's not just these electrons, but you're thinking that, well, I should be using all the electrons, which is actually not, causes some confusion, because as I argued earlier, current really flows due to these. Now, more importantly in the context of this colloquium though is that if you try to understand current flow in graphene, the first thing you run into is like what mass to use, because if you're at all familiar with this literature, you'll know that this is a material in which the EK relation is such that there's no well-defined mass as such. That is, when you look at the EK relationship, as you know, usual semiconductor have a parabolic relationship which you write as E equals h bar square k square over 2m. But that's not the way it looks like in graphene. And then you would have some density of states down here again. Okay. And current flows if there is a density of states available around the chemical potential. And the other thing I've sketched here are the two Fermi functions. That is, when you separate these electrochemical potentials, because each electrochemical potential actually describes a Fermi function. And this Fermi function you have seen before looks something like this. And for mu1, it changes from 1 to 0 right around mu1. For the other contact, it changes from 1 to 0 right around mu2. Everything below this is filled, above it is empty. Now, why does current flow? The way I think about it usually is that this contact wants to fill up these states because it's below the chemical potential, wants to fill them up. This contact wants to empty them. And so what happens is it keeps filling it up and it keeps pulling it out. And that's why current flows. And that's why if you don't have any states here, no current will flow. Why don't these states contribute to current flow? Because that is one question that often comes up and causes a lot of confusion, is that should these states contribute? And what I'd like to argue is, in general, not really. Because when you consider a state down here, this contact wants to fill it up. That contact also wants to fill it up. So it just stays filled. Nothing else happens. That's all. You see, the reason current flows is that as far as these states is concerned, the two contacts have two different agendas. One would like to fill it up, one would like to empty it. That's the basic. Okay. Now, The usual way of thinking about current flow, though, the formula that you are probably familiar with, that's this one. That's the Drude formula. And this is what is usually what you carry in your head. Like if you're trying to understand conductivity, you'd say, well, it's proportional to the electron density and it's proportional to the mobility. And where does this formula come from? Well, the way you usually think about it is that if you think of electrons inside this material, the Newton's law would say that dp dt is the rate at which the momentum changes is equal to the force exerted on the electrons. And I'm not worrying about this minus sign. So, I mean, you could put that in there, minus q, but you could think of q as being a negative number for this discussion. So, it's dp dt is equal to the force. Now, if you believe that, then of course the momentum would keep increasing with time. What you say is inside a solid, that's not what happens. There is always some scattering term that does this. And so there is always this friction. And so at steady state, you can drop this. And so the momentum is equal to q over tau, q tau times E times the electric field. And then how do you calculate the current? Well, the usual approach is you write current is equal to Q N V. This is the general equation for calculating currents. It is the charge on an electron times the electron density per unit length. It's the linear density of electrons times the speed with which it is moving. So if you want to calculate current there, you see you need the V, and so you put from the P, you try to get a V by putting a Q tau over. It looks linear, looks something like that. And then of course, it's confusing because you don't quite know how to extract a mass out of that. So that would be the first problem you'd run into in terms of trying to apply this equation to graphene. Okay. Now instead, so if you look in the literature, no one really tries to use this at all. Although this is the one that we all carry in our head, this is how you interpret experiments, this is how you think about things, yet this is not what anyone applies though in this field. What they apply is something else, and that formula looks something like this. And this comes from, they say, the Boltzmann equation. So the equation you'll see most often in the literature, they will say that, well, what you get from the Boltzmann equation is the following: q square times so this is the same Fermi function, and here, by the way, we are talking about relatively low bias. For everything we'll discuss, assumption is this voltage is small, so we're really talking of linear transport, nothing to do with any nonlinear issues at all. Okay. Now, so this F is basically what you'd have at equilibrium. That's the F that you use here. And this D is the density of states per unit area. So I'll usually define the density of states as the density of states just per unit length.